All right. First thing in the morning, let's do some code talk. It's going to be a little dry unless you really like assembly language, machine language, creating a binary code, and reading text and parsing lines of code. So, everybody, woo!
You gotta work on your salesmanship.
Yeah, I don't like to oversell. You know.
Well, you've undersold, so let's over deliver.
Okay. Today is all about how an assembler converts text into machine code, basically. So yesterday I did a talk on the editor. So you create your file, you have all your instructions, and now you're going to have this program read that in, convert it over to an assembly language file so you can execute it. I like to start with, maybe I'm not going to start with anything. Sorry about this.
Monkeys with typewriters.
Woo, woo. There we go. I always like to start with definitions. Assembly is low language programming language to generate CPU instructions. Machine code, a set of instructions coded so that CPU can use it directly. Resident assembler, an assembler that's in the computer that you're working on. Cross assembler, an assembler that's in a computer that you're not going to execute the code on. Macro, that's in your text files, a group of text instructions that are used as a group. So when you say, I want to use this function, it'll go read the macro code and compile it. Macro assembler is a assembler that can process a macro file. Source code, human readable instructions program language, the thing that you created to tell it to create a machine code. Object code for the CoCo, it's just a straight binary file. So we're not going to be doing any linking or storing and relocating later on by modifying this. This is just going straight to the object code as a binary file. Memory, any place in the 64K, so I'm not looking at CoCo 3 capabilities. And the screen is the standard display that's created by the 6847. The display was more important in the last one, but this one we're going to be outputting stuff too. So when I say it's going to display, it's just going out to the regular screen text. Okay, for the assembler to work, it's got a couple of different kinds of files. It'll have a text file, the sequential ASCII characters that's from your code that you created, and then it's going to have the binary file that the machine code is on, but it's going to have types of files that are used. So you're going to have your main program file, which is the one that you're assembling, and then you can have an include file. So if you're running in your main and you say, okay, at this point I want to add another file that does input outputs or something like that, does keyboard readouts, rather than having to make sure it's all in one continuous file, you can have an include file. Let's see, we talked about the output, and another kind of output is the macro assembler lets you create a listing file, which it doesn't have any kind of really serious controls on that one. It's just you tell it, instead of going out to the screen, I want you to go out to the printer, and not the printer, out to a file number, and it'll create a file and send it out to the file. The easiest way to jump into this, in my opinion, was to say, okay, instead of looking at how it takes the whole thing, let's just go ahead and take one line of code and we'll break that apart and see how it handles that. So if you've got a line of text, you've got the basic elements, the label, the operation, the operand, and the comments. So when you look at this, the assembler analyzes that line of code, parses it out, figures out what to do with it. A couple of basic lines would be a blank line. It looks at it, it sees no characters and a terminator, and says, okay, this is just a space, I'm just going to move on to the next line. The other one, it looks at it and it sees an asterisk or a semicolon, and it says this entire line is one gigantic comment. So it's not going to process that other than if it's got to print it out to a print file or print to the screen or something like that. But that's just basically you saying, this is just for me. And when it goes through the assembler, it says, okay, good, that's just for you, so I don't care. A label is used to reference a specific location in code. So when you put together your code, you'll have, let's just say E00 because that's where most codes start, and a lot of people will use the term start right there. So when you have a label, it'll define that label as E00. So it's a 16-bit value that it'll use for that location. The operation, that can be a couple of different things. We know about opcodes, so load X, load A, store X, push, but then we also have pseudocodes. So you have a mnemonic that is for the assembler. So you would say something like MACR for macro. So you say, assembler, I'm doing a macro instruction now, or command of list, or something like that, where you're taking control of what the code is going to be by what the assembler expects. A couple other examples would be like FCC, FCB. Those are all pseudocodes. If you have a macro name, it'll start working on the macro. If you've already defined it, it'll look it up and it'll use it. If it's not been defined, it'll let you know not found in macro. So sometimes you'll do a spelling error when you create your macro, and it goes out and it looks and it says I can't find it, so it'll say macro not found. And sometimes that's just go back, check your spelling, that kind of thing. And then the code substitutions. Those are kind of left over from going from 6800. Sorry, I'm trying to get technology working again. 6800 to 6809. There we go. These are the code substitutions that they recognize in the Microworks. And like ABA is add B to A. And like I said, these are old 6800 codes, but then they do nice stuff for us like clear D. So you could say clear D, it'll clear the A register and the B register. These directly substitute these code items instead of having you type out like neg D. I could do com A, com B, sub D number FFFF minus 1 basically. Rather than having you type those out or put those in as your own macros, you've got a direct code substitution. These are the pseudocodes that the Microworks uses. So like I said, there's FCC, FCB, list, the include instruction. All of those are in the documentation for the Microworks. So you don't have to have full knowledge of this. You can just go look and say, hey, what can I do for this stuff? And I think that was it for this one. Okay. All right, I'm back. So let's see, opcode, pseudo, micros. Yep, that was it. So this is basically line of text. I guess at this point, before we go farther, I'd like to ask, does anybody have any questions about how we're gonna approach this line of text as far as how it's divided, what we're looking for out of it? We're good? Okay. So now we're going to go down into the next ring of hell. The operand. When you look at these operations, they have a lot of characteristics. When it looks up in the table, there's not table, it's a data tree that stores the type of macros, or not macros, mnemonics. The type of mnemonic it is, they have control bits in there that identify what those opcodes do. When it looks at it, it'll know, is it an inherent operation, an immediate operation, an extended direct, a register operation, a relative operation, relative indirect, extended indirect, or an absolute indirect. These are all terms that are right out of the 6809 data book, data sheet. And when you have an opcode or mnemonic, it could be any of these modes, might not be some of these modes. Some of the mnemonics, they actually will let you say, okay, I'm going to do a direct addressing mode. I'm going to let you do an index address, so they can do a lot of different addressing modes. The first thing that this is going to want to do is when it grabs that operation, it's got to determine how to handle that processor or process. The most complex one, if anybody's ever looked at the index addressing modes, there's a slew of ways that you can handle that. The basic list is the 0 offset, a constant offset, accumulator offset, an auto increment, auto decrement, indexed indirect. Yeah, that was it for those ones. Whoops, going crazy. So when you analyze your operand, you're going to look at that and say, okay, how am I going to modify the opcode? And these are all different ways that they can be done. Okay, so that was just a description. That wasn't anything really in depth about it. But when you assemble the line of code, the way that the Microworks does it is you go to AC line at 1114, and what it does is it goes in, it resets values. It says, okay, the current effective address is the program counter value. The machine code address is the program counter. It clears the halt, resets the output byte counter to 0, because when you assemble a line of code, it has a counter. It says how many bytes are going to go to the output file. And it says, all right, I'm starting off at 0. And it clears the default label value. So the label value is kept track of when it assembles a line of code. So when it goes to the next line of code, it says, all right, that's now 0. We're starting over with a new label. And if there's not a label, we won't define it. And let's see. And we talked about how it does a complete line if it's a comment. So it first starts off, like we were talking about, evaluates label field, operation field, operand field, and then comment field. And we kind of mentioned that before. Oh, that's, I guess I should have started off. This is all based on the Microworks assembler. And the reason why I'm doing the presentation is I did the unraveled books on them. And if you go to the assembler unraveled, it has all the addresses and all the labels. So occasionally I'll have something like here, the AC line. That's actually address 1114 in there. And it's the thing about the Microworks is it was made to be position independent. So depending on how much memory you need or how many disk files you want to reserve, it can shift it. So that number will change. But yeah, the label starts there. So if any of you are interested in this kind of stuff, I've got the unraveled for the editor and the unraveled for the assembler, and I have a flash drive that has that and a couple other resources on it. And as background, when I was working on this, I found that I was getting a little lost, going like, well, wait a minute, this isn't in the documentation, this isn't there, and I couldn't figure it out. And last CoCoFEST, I grabbed LWS tools, went over there and talked to, his name's not LWS Tools, but William Aswell, there you go. Talked to him, it's like, I can't find these things in there, what's that for? And he's like, well, I think that might be for this, and he had some random stuff. And I wound up going over to Brian Weisler's table, and he had one of these on his thing. And he has the XOR machine from when Kilgus was setting up. And this is the manual that Motorola put out for that assembler that's in there. And when I went through and looked at this when it was on display, I found those commands that I was not able to find. So it looks like when the Microworks made their assembler, they tried to copy this command for command, opcode for opcode and everything. But when they started putting it into the CoCo, as they were jamming it in there, we don't have room for that. Let's just leave that out, and we'll work on it later. So they still left a lot of stuff, but when I traced it out, it all pointed back to creating a new macro. So they might have been thinking, okay, in the future, we'll just make macros for those functions or something like that. So But yeah, thanks for asking, because I completely forgot to introduce the subject matter. So yeah, when it goes through and it evaluates these lines, it has that one point where it says, I'm pointing to it with the Y register, go to this address, and it'll just take that line, crunch it out, and make it into machine code. Okay, when it evaluates the label field, so now we're going to get into the details of the parsing. It looks at the characters. It always has to start with a capital letter. So if it sees a number, a period, all these different characters that may be in a label, or if it sees something that can't be used in a label like an asterisk, it'll automatically say, okay, that's not a valid label, and it'll skip it. But the labels, they can be 6 characters long, and like I said, they always start with a capital. And the third item on there, I've got the valid characters for a label. So you got period, $, underscore, the numbers, or capital letters. And I say capital letters, I plan on redoing the Microworks code, and I want to make it so they can use lowercase as well. But yeah, I mean, I hate where it's like, okay, I can't use the lowercase, I can't do this, I can't do that. But the capital letters are kind of moot for this, because this was made back before anybody even had those lowercase satellite boards. Nobody wanted to make lowercase. So yeah, so that's one reason why they're all uppercase. But if it looks at the label, says it's a valid label, goes and looks it up, can't find it, it'll say, okay, I'm creating a new label on this run. If it looks at it, it can't find it, then it'll say, is it a macro? So it'll look at the macro, the local labels first. So a local label in the Microworks is just a letter and then the @ symbol. So if it says, okay, I found a capital letter and I found an @ symbol, now I know it's a local label. And the thing that really caught me on assembling this stuff is I was thinking local labels were created as you were assembling the code, because between spaces of code, that's where a local label would reside. And I thought, okay, it's going to create a local label, use it here, and when it's done, it goes away forever. They actually encode every local label to be a permanent label, and it saves any local label that you created. So if you just went through and just said A @ B @ C @ and you went through the whole thing, you would be creating labels that it would store even though you didn't need them in the future. I think that might be something I want to get rid of in the future to save on label space, because like when I tried to compile the assembler using the Microworks assembler, I had to switch over to LWS ASM because it couldn't handle the number of labels it was storing. So anyways, that's a little bit of rambling stuff about local labels. And so then if it can't find it, or if it's not a local label, then it says I'm going to do a macro, macro local label, which I've got on there / period, and then in 2 letters. So if you're inside of a macro and you want to create a local label that's not going to be seen by the outside one, you can do that / period and create a local label. In taking apart the way that they handle their labels, though, it's not really necessary, because they also keep track of regular local labels in macros. so you've got so many label variables that it's creating and storing in memory that I just don't know why they didn't just say, you got local labels and macros, just do what you want. We're not going to do this special thing. And the label configurations, as I was trying to describe, if you look at a standard label, it starts off with a capital number or capital letter, but then you can have any of those letters on there. C0 is always a capital. C1 through 5 are optional. You can have more than 6 characters if you tell it to enable long labels, but it really just truncates the first 6 off. So the the first 6 characters will be saved as label values. The rest of them are just ignored. So if you create a label that has 6 characters that are unique, and you create another label that has 6 characters that are unique, but you add one more to it, it's going to think it's the other label. So I always just say, hey, I'm not going more than 6. And I put on there examples, or like start, frog, in string with different characters and stuff like that. So you could see, hey, you can be as creative as you want with how you configure those together. And then I said the local labels has the C0 as a capital letter, C1 is the @ sign, and C2 through 5 are not used. The macro label, the / period, and then 2 characters, and then the rest are unused. So you can see local labels A@ through Z@, macro labels \, and then 2-letter combinations. Like I said, I don't know why you would have a separate macro label after looking at it, because they're essentially the same thing as a regular local label. The only reason I would think is you can, when you print listings, you can expand macros, and it may confuse you there. Yes, sir.
I was just going to ask that if you list it, does it still show the things that it's chopped off?
Right, yeah. It doesn't produce anything in the listings other than what you typed in. And when it does the evaluation, that's all internal. So if you said an 8-character string, it prints an 8-character string. Internally, it only looks at the 6, but because you typed 8, it's going to display or print 8 on your listing. And now that I stumbled across it, I think macro expansion would be the only place where it would be an issue, because when you expand macros, it'll show you the listing, but if you don't expand it, it'll just say the macro name you gave it, and then parameters if you set any. But if you expand it, it'll put the whole thing out there, and that might be where, well, I see an A@, and I also see an A@ that was generated by the macro. I don't know. I still think that's a programming preference. Okay, the operation field. I put these things, like I said before, with the name and the address for the book, but the mnemonic descriptors are looked up, and then it creates an opcode pre-byte. It's, if you look at it, like if you do anything with the Y register, it requires a pre-byte saying, okay, I'm going to use a different instruction set because I'm now using the Y register or the U register or something like that. And encoded into the mnemonic descriptor is a instruction saying, yes, generate a pre-byte. So that's built into the mnemonic descriptor. Okay, I've got on here, process operating field using mnemonic descriptor at R11B9. That's going to take the control bytes that are in the descriptor table and say, I want to do this, which is going to be indexing. I want to do this, which is immediate, 8-bit, relative offset and everything. And that's kind of what's listed down there. The control numbers are what will get you there. And I've got it in here later. But let me see. Oop, page up. Sorry, I'm going to page up through the code here. In chapter 9, basically this is the mnemonic record, and I'll show this later on. But if you look at the first byte, or the record descriptor, mnemonic control byte, that over there has the length and the opcode number. The second one has the condition byte. The third byte is the operation byte. The condition byte, or sorry, the control number comes from the control byte. And if you see, there's 16 different possible things that you could do, and all of those are listed there for if it's creating a macro, if it's inherent, 8-bit operation, CRC operation, jump subroutine only. So it's encoded into the mnemonic descriptor as to how you're going to handle that. So you don't have to look at every single opcode and say, all right, do I have to do this? Do I have to do this? No, it's the opcode descriptor tells you this is how to process this, and we get 16 different routines to do the processing. That way we don't have to have one gigantic routine that covers all of them. So that's the item 4, talking about the 16 different operations. And now it wants me to click again. There we go. The operating field. Trying to think how to describe this. You've got the ability to do the opcode. Like I said, we got opcode, pseudocodes, macros. That's kind of a recap there. But based on the way it's handled in there, if you've got like code substitution, if you look at the mnemonic descriptor, it basically gives you an offset, and it says how many bytes are going to be code substituted. If you say, I've got a, like I was talking about the negd, I've got the negd command, it'll say, here's how far it is in the descriptor table offset, and here's how many bytes I'm going to copy, or this is what it's going to do, I guess I should say. So it'll copy it byte for byte until it gets to the end. That way you get a complete 100% code substitution. So if you wanted to, you could make up your own permanent opcode macros and put them in there. But this is just kind of a recap, because I think I pretty much explained how it looks at the opcodes already. Let's see, no zeros allowed in the opcode, and ends with a null terminator. Yeah, so that's basically a description of the opcode descriptor. And this is a chunk from where I was just at, talking about in chapter 9 of the book. And like I said, if you look at the condition bytes, you can see their bits 3 and 4. If you've got those set, you got to do a pre-byte of 1-1 or a pre-byte of 1-0. That's a whole lot easier than trying to figure out from a table of these opcodes would produce a pre-byte. So they just encode it into there. The other weird thing that they do is the opcodes with an L get the L stripped off, because there's load, LEAX, long branch, and they just did it for simplicity's sake. Is say every opcode we take off an L, but we'll add a flag in the descriptor that says this opcode is supposed to have an L. So if it doesn't have an L when you look at it, it's not the right opcode. So when it looks at it, instead of seeing like LDA, it'll just look for DA. So these get alphabetized too. So there's a D section for mnemonics. So it looks in the D and it says, okay, I found DA, and it's flagged with an L, so LDA, that matches what you asked for. So that way they save on some bytes, and they also save on some requirements that would say, oh, well, this is a branch, and it's also a long branch. Well, now we can just say, here's a branch, and the bit says whether it's a long branch or a regular branch. Okay, the operation field. After you do the opcode, you're going to either have a stack, a register, or indexing. If you do a stack operation, you're going to have a list of registers. So if you have it coded for how many bits, or each individual bit for each individual register that's on the stack, you'll be able to say, okay, I'm going to push A, B, C, C, X, and it'll figure out what the bit orders are, and it'll create that bit. If you're doing a register that's an exchange, it'll do the opposite, where it says, okay, I'm expecting one register and another register, so I'll come up with the first 4 bits to identify which register they're exchanging, and the second 4 bits to identify the other register that it's exchanging, and create 1 byte. And it's really register operations, but it's all encoded in whether or not you're breaking it up 4 bits to identify a register or 8 bits to identify any register. The one weird thing that I found when I disassembled it is they let you use immediate addressing with push, pull, and exchange. So if you were sitting there doing coding and said, I want to push, but then you said number and you put a bit pattern for what you wanted to push, it accepted it. So I guess it's the old days when people were looking at direct CPU code rather than doing assembly. Yeah, I know I'm pushing A, so I'm just going to say pound 0001, you know, that kind of thing. So I thought that was kind of interesting. And the indexing, we talked about that before with the zero index, constant index, accumulator index, auto increment, decrement, and index indirect. And these are the references out of the 1609 manual that covers it. And like I was talking about, this would be what you do for a push-pull for the bits. And this is what you would use for a exchange or a transfer, one register to another. And this is the pattern that you want to build when you're doing an index addressing based on these things. And this is another way of indicating it. So they've got direct and indirect, and then they've got how many bits you're offsetting, are you auto incrementing, decrementing. And I like that one, but this is a nice quick reference. So you can say, oh, I'm auto incrementing once. I shouldn't see anything in those lower 4 bits, you know, that kind of thing. Yes, sir.
In the previous slide, you mentioned that potential duplicate stack operations would be ignored.
Mm-hmm.
Does that not create a problem if you're trying to trace your code and it simply skips over something?
Okay, I might
Yeah,
not have said it very well.
Potential duplicate registers will be ignored.
Oh, yes, yeah. Potential duplicate registers in a stack operation.
Yes, so if you make that mistake of putting it in your text file, then when you're trying to trace the error, there's not going to be anything there at all.
Right. What it does is when it processes, it has a list of the registers and the bits, and it'll go through and it'll say, okay, he's looking for register A, and it'll find A, and it'll say, okay, that's going to set bit 0, so it'll set bit 0 in the temporary one, and then it doesn't care after that. It'll go through and do another scan for the next register that's in the list, and if you have A, comma A, comma A, it'll just say, okay, or 001, and sees it again, or 0001. It doesn't stop to say, oh, you have a conflict because you have duplicates.
So the conflict is ignored. All right.
Yeah, and I wish that they actually checked for it, because you could be sitting there thinking, okay, that's in the A register and B register, but you type A, comma A, because something in your brain is locked in on the A register, and then when you assemble it, you're sitting there thinking, okay, A, I don't see a problem with this. He didn't ask for a Q register, so I'm not going to give him an error, but you've got a duplicate, and it just ignored it. So that happens a couple of times in the way that they process their code, and it's basically because the way that they approach it is they're looking to create a bit pattern, and rather than check the entire sequence of characters, they take the bit patterns that are produced by each individual letter, and then they just start over again at the beginning. So like if you said transfer A, comma A, that's a legal command. You know, you're just basically creating a no-op, but it's not going to give you a warning saying you do know you're not doing anything other than keeping A what A already is, you know. So those would be nice warnings to have, but they don't do it on this one. They just scan for appropriate registers, and they set appropriate bit values. So that's what we do for that's what they do to ignore it. They just don't pay attention, you know.
Thank you. That clarifies it.
Yeah. Thanks for bringing it up. I glossed over that completely when I looked through that list. Okay, let's see. Now that we did the parsing and the assembling and went through all the opcodes, now we can go back and say, okay, moving out, looking at passes. It's a 2-pass assembler. So the first time it goes through, it immediately clears out memory, clears out variables, clears out flags, any inputs that you give it. Like if you say, I want to see a listing, I want you to warn me if there's any branches too far, all these kind of things. Sets up all those flags, but there's no code, no labels, nothing. And pass 0 runs through, and anytime it sees a label, it creates a label value. Anytime it sees a macro, it creates the macro structure. It doesn't actually produce any code. So the only thing it does is it keeps count on how many bytes, where you're located at, so that it can assign label values. And when it goes back through the second time, that's when it'll do things, and it'll say, okay, well, he said store X at this location. Well, I have this location now because of pass 0, so now I know what value to put in there. So now you've got defined values, defined variables. At this point, when you hit something that's a macro, it'll actually go through the macro, do all the assembly on it rather than just create the structure. Let's see. Sorry, I'm not fully rehearsed. Yeah, after pass 1, closes all the file and it returns a basic. So really, it's kind of like pass 0 is a dress rehearsal. You know, pass 1 is the actual, we're going to create a code. Does everybody understand the concept of pass? You know, when it does a pass through, it's just running through the code trying to create something.
As I understand it, labels have to refer to an address.
Right.
And so in the pass 0, they set aside a space to put the numerical value in, which they do in pass 1 after they see where all the labels are.
Right. Yeah. Yeah. The labels are the address, and they are all 16-bit values. So when it goes through pass 0, it will create a 16-bit value, store it in the label list, so that when it goes through pass 1, it will be able to say, I'm not calculating that. I can just grab that 16-bit value, use it for an address. I can use it for a counter value. You know, so if you've got something that says, you know, okay, load D number whatever, and it's the symbol. Now instead of an actual number, you're actually going to get that symbol value. So it's always 16 bytes or 16 bits though. Okay, did I skip one? Okay, yeah. So when we first start up the assembler, before we do any of the passes, they said moving out past the part where we're actually doing the assembly. It starts at the memory use is initiated, and what they do is they say, okay, I'm going to take after the basic variables, all the way up to where the stack starts. That's all the free available memory that you have in the entire computer. So they say, I'm claiming this as mine, and I'm going to set it up so that I can do what I need to do during the assembly process. The first thing it does is it takes the very top and it says, I'm going to reserve 128 bytes just for me. So it actually moves the stack pointer that BASIC has down 128 bytes so that it says, now I've got my own stack that I'm not going to conflict with BASIC, and I can say this is the beginning of my variables below that stack. So it's setting a hard break, saying this is stack that's above, and below I've got these other variables. And the rest of it is essentially a heap where you have a big pile of memory, and everything that needs memory is going to go there and use it. And the start at the bottom, they reserve that for the user stack. If you have during your program, you say, I want to save these values onto my user stack, do some program manipulations, change something that I would have used those variables, and then after that, you can pull those back off of the user stack, so you can actually change values during your assembly process. The 16-bit value that you assigned can be reassigned now because you're pushing them off on the stack, and you're going to be able to change them. They also have the ability in there. One of the mnemonics is ask. So, well, there's ask and message, which usually work together, because if you say message, you can print something on the screen, and it just prints it on the screen. But when you say ask, you're waiting for an input. So if you say, how many colors should this be? And then your input would be a variable colors or something like that. And you say, ask colors, whatever they type in, that becomes that symbol. So you can have one routine, and you can sit there and say, okay, well, this time I'm going to make it for 8 colors. This time I'm going to make it for 4 colors, 16 colors. It's a way to give you some kind of flexibility in how you're going to create your code and how you're going to use your variables. And that's the stack is at the very bottom. And then after that, that's where everybody starts really competing for locations. And it's not located here, but I'm going to go ahead and move to it. Whoop. Yeah, there it was. And this is just so you could see, this is the normal conditions, where you got the 128 byte stack for the assembler. This is the input descriptor stack, which we'll talk about later. It starts off at 50 bytes. And you got a label array, which starts off with 0 bytes, the free RAM, and a labeled linked list, which starts off at 0 bytes, and the macro array that starts off at 0 bytes. So when I talk about the heap, I'm really talking about everything from this red all the way down through this black. These guys can grow. So you can have the label linked list, it can grow. The label array, that can grow. The input stack descriptor, that can grow. The macro array, that can grow. And it has to shift around when you call on that resource. You say, I want to add macros. It has to be able to handle that. And that's done a little bit later when we talk about memory processes. But this was basically that little block that I showed you. That's the memory initialization, setting those all up to zeros, except for the user stack, which is 100 bytes, and the heap, or not the heap, the input descriptor that starts off with 50 bytes. Okay, the user stack is constant. They never change the value. When you start the assembler in the basic routine, they poke a value into the memory of the what would you say, the operating memory of the assembler. When it starts its memory initialization, it looks at that and it says they want, if you say I only want 5 things that I can store on the stack, it'll reserve 10 bytes of memory, so you have 5 words of data that you can store. So if you're looking to save memory and you know you're not going to use the stack, you can just tell it, say I want 0 of the user stack, and that'll give you 100 bytes of memory that you would have lost. But it never changes. The values for all the other stuff, those things all change. The stack pointers all change. Okay, so now I'm going to jump into the kind of scary stuff. Adding macro records and macros to the list. When you're running the assembler and it sees a macro, it wants to store it in that lower part of memory. And if you remember looking at that one, it has other stuff around it. I'm trying to think of how to describe this best. Yeah, I think what I'll do is I'll go to that one and I'll just describe it. Okay, if you're increasing the macro, because reading that slide, it's a whole lot easier to see this than it is to read that. This is where we normally are. Well, now we want to increase the macro. We got the linked list laying on top of it, and these guys are all linked together. It's a data structure of a linked array. If you want to increase this, you got to get this out of the way. So what it does is it takes that, moves it up to free RAM, And now it can add to the macro array up into the free RAM without interfering with anything else. And then when it gets done, it brings the linked list back on top of the macro array. And when it does that, it has to change all of the pointers because they're all pointing to each other and everything like that. So it'll go through and it'll realign all the pointers inside of here. But if you needed to, this sucker will grow and take up that whole space. So every time you create a macro, you gotta remember you're using part of your heap. So if you want to use macros because they save you memory, they save you labels, that's perfect. If you're using macros because they're convenient and you like them, they may be eaten into the amount of free space that you got to create code. So you got to make a decision based on how you're going to affect that space. Did that make any sense? Because it's kind of weird to take one data structure, move it someplace else, change another one, and then move it back and realign everybody. That's essentially what we're doing. Okay, so that was adding the macro records number 2. And number 3, adding a label. I'm going to do the same thing. I'm going to jump over to this thing. If you look at where the labels are, they're right on top of the free RAM. So adding a label is no big deal. Just eat up some more of the free RAM. So the linked labels and the label array, these are the most commonly used ones. And I think that's why they put the free RAM right in the middle, because they can say, I got a new label. Okay, I'm adding a new linked list to my label, which the linked lists actually have for cross-references. So it keeps track of every time you use a label. So you can work labels all you want. In the middle there, it's just going to suck up that free RAM. And I've got on there the cross-reference label. That's number 4. That's what I was just talking about there, where it's on the other side of the label. And basically, they just go ahead and say, okay, when I add something, I'll create a new label record at the end in the free RAM, and then I'll make a link to that one. And that'll be the new termination for the link, and it'll take over as the top cross-reference. And the way they handle the cross-reference that are in that link list, when you assemble and you want to know every time somebody uses that label in the whole program, that's what that's really for, so you know which addresses are using that label. If you run out of memory, it just stops increasing that cross-reference. So it's just there for reference for you, for debugging, for looking back and tracing code. So that's kind of their, hey, you ran out of memory, we're just not going to do this anymore because you don't need it to actually assemble. So that's the one thing that's different. All the other ones, if you run out of memory, you can't do them anymore. And then this is the one that I kept referring back to. The only one that I didn't do was the the descriptor. This guy down here, he grows in 50-byte increments. And we haven't even talked about him. We'll get to him later. So if he needs to grow here, he's got the labels in the way, so he does the same thing. He just moves the label array down, gives him 50 more bytes, adds the 50 bytes on there, and that'll all become red, and the label array is now in a different location. So this guy doesn't need to do any kind of linked list or anything like that. He just tells the assembler, this is where the labels start now. And then it'll also tell him, this is where the input descriptor stack ends. So now you've got an added piece of that up there. So that one just nudges the labels out of the way rather than having to relocate everything. Okay, so input file descriptor. It's kind of like a big valve for the code. When you bring in your stream of text, the input file descriptor decides what it is. If you bring in your initial file, it says, okay, you're type 0, you're the initial file. When I bring in a line of text, I'm going to put it in there, and then I'll send it off to be processed when it gets done bringing in an entire line. If the assembler has an include instruction to get another file, it'll go out and get the line from that other file, store it in the input file descriptor, but it'll flag it as a type 1, which is the input, which is a include file. When it gets all done doing all the include file, it'll say, okay, that file's done. It'll close that file. Now I'll go back to the previous one, which could have been another input file. So you could have had nested 2 or 3 includes. It just keeps stacking them up in that stack, so that rather than saying, okay, here's a file, here's a file, here's a file, it's bringing them in like a bellow, and then it's pushing them out to go for processing at the other end. It also has the descriptions for a macro. So if you're doing a macro, it'll be a type 2, and when it sees a type 2, it knows it's processing a macro, and all the other processes in the assembler will see, okay, I'm processing a type 2, I got to do this, where it'll start looking for information it didn't have before, like the local macro labels and things like that. Those aren't enabled unless you're processing a type 2 line from the input file descriptor. The other thing would be a type 3 would be the macro parameters. So when you do a macro, after you do the macro command, you list off parameters. So you don't have to, because it could just be a straight, clear D macro or something like that. But if you said in a macro command and you wanted to use certain variables, they come after the macro command, it creates type 3, which will list off all of those variables that you put in there. So it's in there running the type 2 for the macro, and then all of a sudden it says, well, wait, I need a variable, and it says, okay, go back to the type 3, grab a variable, input it, and we'll push that out to the code. And it's kind of a, when I discovered this, it was like, oh my God, because it's not just I'm selecting this and I'm sending it off to the file. It's I'm pointing at this file, I'm sucking it in as much as I need to send the next stream, and I'm going to grow that buffer as large as I need to in order to accommodate that. And that way, when I switch over to output it to the processing, it's sending it out in one continuous stream to the assembler. Does it make sense at all what I just said? Okay. I guess that's kind of why I did the red type there. I'm like, this is why I called it an input file descriptor, because it describes the input file and it stores it and it saves it in the buffer. So I call it input file descriptor stack. Okay, and this is just a breakdown of the different characteristics. Like I said, type 0, that's your normal input file. That's the one you started with. It's closed when that file is empty. When it's empty, you're done assembling. So that's the one thing. This is where you start off. This is your root. Type 1, that's an included file. So it does the same thing as a regular type 0, except when this one's closed, now it tosses back to the assembler and says, okay, I'm done with this file. Close it out. Let's go to the previous include file. Let's go back to the original root file. And macros, the way that they work with the input file descriptor, when it sees the keyword macro, it executes the pseudocode for macro, and it says, I am going to store every single thing after this as a macro in the macro file. But when it reaches the characters end m, it knows that's the end of macro, and it stops reading it into the buffer for the macros. It also has a detection in there for end m as a pseudocode, because end m only belongs in macros. So if you do an end m outside of a macro, it'll say, I can't because I'm not in a macro. When you're actually processing the code, and it's reading a macro, it's kind of the opposite now. Now when you say macro, the input file buffer will go to the macro records, store it in the buffer, put the parameters in the buffer as it needs to so that it can output it to be processed. And that's kind of a graphic description of what I was just saying. The descriptor buffer, that thing grows and grows and grows. It never shrinks. So once you use some space, it'll never give it back. And it just keeps on storing up information as you need to so that it can squirt it all out at the other side. Okay, so that's memory. Now get to work with expressions. Whenever you look at a assembly code, you'll see something like load a number $, or store a vector tab. Each one of those is an expression. And the assembler has to figure out what to do with it, because it doesn't mean anything to machine code. So when it looks at it, some of the stuff I've got on here, you can see if there's a apostrophe, it's a character. If it's a ampersand, it's a decimal value. $, hex value. %, it's a binary value. At, octal, start brace, subtract, plus, and multiply, or no, oh, current program value, sorry. An asterisk is actually will grab the current program value. That's why you see things like EQU asterisk. It grabs whatever that current value is in the program counter and stores it. So the symbolic elements, it looks at those characters. So if it sees any of these in the string that you're using as an element, it immediately says, okay, I know I have to evaluate a decimal number, or I know I have to start a grouping, and I know I'm just going to grab the current program counter. After the string, there's a couple other ones too, because the convention is at the end of a number, if you put B, it becomes binary. At the end, if you put Q, it becomes an octal number. And if you put H, it becomes hex. I don't know why we do this. It's like, to me, it's like pick one or the other. It's like put a $, at the beginning, or a ampersand at the beginning, or put an H at the end. But we give the option for both. So it actually processes the data based on what's at the beginning or what's at the end. And the math functions, multiply, divide, and exponent. So as you start evaluating the expressions, it'll, like if it looked at a number and it said, here's a hex number, and I'm going to store that 16-bit value on the stack as it's processing, and it sees, oh, I'm also going to multiply. Well, now I'm going to do another expression evaluation, because that is going to have to be converted from whatever character set, number values that you gave it into an expression, and then you do the multiply function. Same thing on here. I've got the logic functions for and, or, exclusive or, logical shifts, and rotates. And then the final one that I've got on there is math linking, where the way that the expressions are evaluated, it's always like in algebra class, how you start with the highest order and you work your way down. Adding and subtracting is essentially linking. So when this sucker evaluates an expression and it gets down and it sees an add or a subtract, it's like, okay, this is a whole nother number. Set it aside, starts over new, because when it gets done with this one, which might have multiplication and exponents and logic, when it gets done with this one, then it's going to add it to that other one. That's what keeps your order of operations in alignment with the assembler. And let's see, expressions of evaluations. The way that it does it is, like I was talking about before, if I evaluate an expression and I get done figuring it all out and I want to do something else because I'm going to add or subtract, I need to have it stored someplace. So the first thing it does when it goes into an expression evaluation is it creates a 16-bit user stack. And that's where it stores all the information for the evaluation. It takes the S stack pointer, knocks it down 6 bytes, copies that to you, and says, okay, now you've got 6 bytes that you can work with that's not going to interfere with the stack pointer, because when we get done, I'm going to move the stack pointer up 6 bytes. That's going to just get rid of all that other stuff, and then I'm going to return from the subroutines. So it makes space on the stack pointer for a user stack, and then it gives the user stack that space to do its operations. So if I'm doing an evaluation, and I get done, and I see that plus, and I know I got to add another one, I'm going to go do it again. So you'll have another 6 bytes reserved on the user stack. And this can go on as long as you keep adding plus and minuses. It's going to keep adding stacks or user stacks so that it can keep processing those. And then kind of like a house of cards, when you get to the end and you add them all up, it's just going to pull them right off of the stack and stick them together. I don't have a graphic for that, so if you can't see it in your mind, okay. But when it first starts in, the first thing it does, it looks for numeric, it looks for symbolic, and it looks for label. And then, like I said, it'll save those 16 bits into the user stack. And then it starts looking for the math functions. If there's no additional math functions, it returns with a 16-bit value in the D register. Later on, when they want to return from the evaluation, they actually will transfer that to the X register so that the X register and the D register both have the result. And then I give some additional math functions that you can find by looking at the code. Yeah, that's pretty much just what I just talked about, wrapping up the information on the user stack. Okay. Does anybody have any questions about the math operations? Because the expression evaluation is kind of important if you're interested in how an assembler actually works, because this is the kind of like the math package you get with BASIC. It has nothing to do with how to print, but it's all about what you're going to do when you're doing your own evaluations. Okay. So the things that I covered here, they're kind of vague, they're kind of complex, they're not really going as in depth as it could, but there's a lot more that I didn't cover. I didn't talk about any of the input-output functions. So I didn't talk about how it accesses files. I didn't talk about how it prints to the printer. I didn't talk about how if you've got multiple files open, how it'll say, okay, well that one's open, but I'm going to go ahead and open another one so that I can do an include file, because it can load up all 16 of your files if you want to. So you can have 16 files open. I didn't talk about how it closes them, which at the end of a session, it'll actually close all open files and return. Let's see. Multiple includes. Detail of listing and flags. So I didn't talk about how to change your listing based on flags. Didn't talk about critical errors, which essentially there's just one critical error in the whole thing, where it's like if you have a forward reference, the whole game's off and it'll just shut it down. But it's got other things, like if you try to do something that's not possible, it'll actually just put in 4 no-ops instead of your code as a placeholder. So it's like, okay, I didn't do your instruction because it's not possible, but I didn't stop the program. And if you want to try it and see what happens without that instruction in place, you've got it. Those kind of things happen. Let's see, I didn't go into specifically how the macros operate. Didn't talk about the buffers. There's a whole lot of buffers. Like one of the things is when you start the assembler, it comes up and it says the Microworks, the world's greatest assembler, blah, blah, blah. The actual routine that does that is just used once, just to display. So what he did was he said, I need memory. So after that executes, that whole routine that does that becomes my input buffer for files. So there's a lot of things like that that he's done in here that, you know, I did this, I don't need it for anything else. Well, I'm going to reuse it. Let's see. I discussed the code substitution. I showed you the little list, but didn't show you all the details of it. And I didn't show the full mnemonic descriptor tree, but it's not really all that exciting. It's just a whole lot of crap talking about how the mnemonics convert to code. And let's see. There's a little blurb about the book I wrote, a little thing about how you can get in touch with me. So there's my email address. At Discord, I'm just at my name. And I'm over here at table 30 and 31. And, you know, if you want to come over and just nerd out, I mean, we can talk about this stuff. I can show you the different things in the listing and show you how it works and why it does certain things. But that's about it for my presentation. And let's see here, I'm gonna, where'd it go? Oh, it's all the way down, okay. Yeah, that's what the assembly code looks like. And like I said, just, oh, you can't see that, can you? Okay. Has it never shown that?
No, we
Oh.
swapped off to some other screen. We never saw it.
Oh, okay. Well, I can see a lot of cool stuff. You guys can see if you come by my booth. So, other than any other questions, I gotta start clearing out for the next exciting show.
Sir, a summary
Sir.
question.
Oh, yes.
A lot of the shenanigans that you were describing are because it's made to work on a computer with very limited memory.
Right.
Right about that. So that if you had a CoCo3 or something like that running this, a lot of this stuff would not be needed because you could just make all your stacks 4 times bigger or whatever.
Right, and I tried to do everything using the Microworks assembler, and when I got to where I was assembling the assembler, that's where I couldn't do it, and that's where I had to switch over to LWASM, because this was written before the CoCo3, and even on a CoCo3, there's no resources to take advantage of all that memory and everything. So that's one of the things I plan on doing, is saying, okay, I can keep a CoCo2 version, I can keep a CoCo3 version, and I can make a 6309, and I can make a 6309, so I can have 4 different kinds of editor and assembler, and try to create IDEs so that if you want to sit down on an original machine and have all these resources available, you do. And I was talking to somebody and said, well, yeah, you can do it on an emulator too. And I go, yeah, well, you can also take this that you would normally work on and do that on the emulator, and it'll operate at however many, you know, megahertz you make the CoCo operate on your emulator. So you can actually do the assembly in an emulator, or you can sit down at the machine and do it. And what I try to do is I try to make everything so it's real hardware, not, okay, I'm going to make a, you know, like this thing here. Honestly, I'd love to see William Assel do 2 sessions so I could see exactly what he was thinking when he wrote all of his stuff. Because this is the kind of stuff that I'm like, oh, he said a bit. That's awesome. So yes, you're right. You could do this with the expanded resources, but you're going to have to set up the tools for it. And sir, do you have one?
Yeah, so for the Microworks assembler, is it who developed it, and is it still, how do you get it?
Yeah, who developed it? The company's name is the Microworks, And I think they were doing basically the same thing Bill Gates was doing, because they created Forth and they created an assembler, and I think they created 2 or 3 other things, and I think they saw them slipping, and they were like, well, we're not going to be able to make it in that world, so they started writing video games. But I don't know where they went to after about 1984, but their files are on the CoCo archives. So if you wanted to download them, you could. If not making a shameless plug, they're also on this cool flash drive. And like I said, the thing that I like about them that I don't like about using Editasm is these don't require line numbers. So if you're restricting yourself to a 32 byte wide screen, you don't have to give up 6 characters for, well, I guess 7 because you have a space in there for line numbers, and you don't have to go in and edit and renumber or anything like that. Because the first thing I worked on was Editasm on cassette, and then when I got to this, I was working on floppy, and the first thing I did was like, well, how do I type in, you know, every time I typed in a line number, it kept coming back saying invalid label. And, and then I figured out, I don't need those anymore. Yeah, but I used Robert Galt's, I paid him for the last update I think that he ever made to do 6309 disk access Editasm with the CoCo 3 screen and everything like that. And it was great, but I was like, okay, I got either 32 wide or 80 wide. And then every now and then I'm sitting there going like, is that a 3? No, it's a B. And I said, I can't do this at 80 wide. So that's actually one of the things I want to do as well is say, okay, you're at CoCo 3. Do you want 32, 64, 40, 80? Let the user decide what the dimensions are of their screen. But the editor is written hardcore, hardwired for 32 bytes wide. So I'd have to rewrite everything because it's all set up for, oh, well, here's a convenient 32-bit or 32-byte flag that I can throw in there. But no, like I said, I'm going to go back to my cube unless there was something else. Geez, you can tell I work in an office. Go back to my cube. But y'all come by, take a look at it. I got copies of the book sitting out. If y'all want to just pull up a chair and read and talk, I'm open for anything. This is more for fun than a business thing. I'm just happy to be here sharing the nightmare that I've lived for the last 2 years. So yeah. But no, thank you all for